be the product representation of the gamma function that will allow us to show that gamma has no zeros in the complex plane. So let me recall that gamma of s is given by the integral from 0 to infinity of e to the minus u, u to the s minus 1 du for real part of s greater than 0. And we saw that this can extend to a meromorphic function on the entire complex plane with poles at the set of non-positive integers. So I will say let's consider a positive real number x. And for a positive real number x, we'll define psi of x to be gamma prime of x divided by gamma of x. Okay, so you can define this for other complex numbers, but I just want to focus on positive reals. For one thing, that's all I'm going to need, and also because we can be sure for now that we're not dividing by 0, because if you just look at the definition, if s is a positive real number, this integrand is positive, so you're integrating something positive, you get something positive, so we don't have to worry about division by 0 here. Okay, so I'll just remark that psi is called the digamma function. It's just the logarithmic derivative of the gamma function. Digamma function. Okay, so let's differentiate our well-known functional equation gamma of x plus 1 is equal to x gamma of x to get, if we differentiate this, we get gamma prime of x plus 1 is equal to x times gamma prime of x plus gamma of x times the derivative of x, which is just 1. So we get gamma prime of x plus 1 is gamma of x, or is x gamma prime of x plus gamma of x. And therefore, psi of x plus 1, which is gamma prime of x plus 1 over gamma of x plus 1. We can write this as x gamma prime of x plus gamma of x. Divided by gamma of x plus 1 is just going to be x gamma of x. And then this is equal to gamma prime of x over gamma of x, which is our psi of x, plus gamma of x over x gamma of x is just going to be 1 over x. So we have psi of x plus 1 is psi of x plus 1 over x. And we can iterate this. So iterating this yields, more generally, psi of x plus n is equal to, it's going to be psi of x plus the sum from j equals 1 to n of 1 over j plus x minus 1. Okay? And I'll label this 2, and I'll label the definition here 1. And I'm just going to remark that it's possible to show that the digamma function psi is actually increasing. So I'm not going to go into explaining why that's the case, but I'll just remark that one may show that psi is increasing on the positive reals. In other words, we're saying that this is the logarithmic derivative of the gamma function, so we're saying that the logarithm of the gamma function has a positive derivative, or sorry, an increasing derivative, meaning that the gamma function is logarithmically convex. So the logarithm of the gamma function is a convex function. It's like concave up. Okay, so next we can use Stirling's approximation in the real case. So Stirling's approximation for gamma of u plus 1 with u plus 1, or with u a positive real, states that log gamma of u plus 1 is equal to u log u minus u plus O of log U. And you can do better, but this is all that I'm going to need, so I'll just state that. And you can really derive this in the same way that you derive Stirling's approximation for factorials. It's just the same thing, except you think of the, instead of doing a factorial, you do gamma of U plus 1. So this isn't hard to get. And now I'll say let's differentiate.
So this is easy for real U.
Right, for
positive
real.
U.
Yeah, for real. And then later we'll do Stirling's approximation for complex arguments. So let's differentiate 3, and I'm going to put this in quotes and explain what I mean, to get the derivative of logarithm of gamma of U plus 1 is just our psi of U plus 1, is equal to the derivative of U log U minus U is just log U, plus O of 1 over U. Okay, so the reason I have this in quotes is because, strictly speaking, you can't just say that because something is O of log U, its derivative will be O of 1 over U. You could have a function that is O of log U, but it's so wildly oscillatory that its derivative is not O of 1 over U. It turns out that as I stated this is actually correct, and you can get that by writing an explicit formula for this in terms of an infinite series, and you take a derivative of that, and you show that what you get here as an error term is actually O of 1 over U. So I'll just mention that this is correct as I've stated it, even though it doesn't, strictly speaking, follow from what I've written. But
so one question. So are you also saying that if you look at log of gamma U plus 1 and write it as U log U minus U plus F of U or R of U as the error, one actually gets an explicit representation for R of U. And one can differentiate that.
Yes.
And that derivative can be bounded by 1.
Yeah, and you show that it's not going to be something so weird that it gets some weird bound here. Yeah. Okay. So just take my word for this, and we can now put U equals n, an integer, in our equation 4 here, and we'll put x equals 1 in equation 2 to get, here's equation 2 down here. If we do that, we get 0 is equal to the limit as n goes to infinity of psi of n plus 1 minus log n. This is just because psi of n plus 1 minus log n is O of 1 over n, so it goes to 0. And then we can write psi of n plus 1, if we set x equal 1 here, psi of n plus 1 is going to be psi of 1 plus the sum from j equals 1 to n of 1 over j plus 1 minus 1. So this just becomes the limit as n goes to infinity of psi of 1 plus the sum from j equals 1 to n of 1 over j minus log n. Okay. Psi of 1 is just a constant, and we know that this difference here between this harmonic sum and log n approaches Euler's constant gamma, so this just becomes psi of 1 plus gamma. And that implies that 0 is equal to psi of 1 plus gamma, so psi of 1, which we could also write as gamma prime of 1, because psi of 1 is equal to gamma prime of 1 divided by gamma of 1, but gamma of 1 is 1. So this is equal to the derivative of the gamma function at 1, and this is equal to negative gamma. So I think this is interesting in its own right, that you have this little gamma showing up for differentiating the gamma function, but I'm also going to use this by saying let's again put x equals 1 in equation 2. So we'll do this again. And what we get, we'll get again psi of n plus 1 is equal to psi of 1, which we saw as negative gamma, plus the sum from j equals 1 to n of 1 over j, and this is greater than log n. And the way you see that this is greater than log n is, I think we did this on like the first day of class, or the second day or something. You look at the harmonic sum minus log n, and you can show that by a pretty elementary estimate, you show that it's decreasing towards some constant, which you call gamma, And so since the harmonic sum minus log n is decreasing toward gamma, it's always bigger than gamma, and so you rearrange that inequality and you just get this. Okay? I'll call this 5. So I want to use this in order to get a product representation for the gamma function. So that's what I'll do now. Let me define g sub n of x to be gamma of x plus n plus 1 divided by n plus 1 to the x times n factorial. And I'm going to do this so that, let me rewrite this, g sub n of x. If we rewrite this gamma of x plus n plus 1 using the functional equation for the gamma function, we can rewrite it as, let's see, x plus n times x plus n minus 1, x plus 1 times gamma of x plus 1. This all is just equal to gamma of x plus n plus 1. You just use the functional equation for gamma several times, and you see that these are equal. And then again divided by n plus 1 to the x in factorial. And now we can rewrite this as a product. So we'll write this as the product from v equals 1 to n of v, or let me say v plus x divided by v. And then I'll also have a product from v equals 1 to n of v over v plus 1 to the x times gamma of x plus 1. Okay, so why is this true? If you look at the numerators here in this fraction, or in this product, the numerators will give you a 1 plus x times 2 plus x times times n plus x. That's just giving us this part here. The denominators give us a 1 times 2 times times n. That's just n factorial, which is right here. And then this product here is sort of like a telescoping product. You can think of this as like 1 to the x over 2 to the x times 2 to the x over 3 to the x times times n to the x over n plus 1 to the x. When you do all the factor, or all the cancelization, you are just left with n plus 1 to the x in the bottom. And then we have our gamma of x plus 1 right there. So those are the same thing. Therefore, we can solve for gamma of x plus 1, and we'll write gamma of x plus 1 is equal to our g sub n of x times, just take the reciprocals of these products and move them to the other side, and I'll combine them into one product. So I'll write this as the product from v equals 1 to n. Just take the reciprocals of the things, so you get v over v plus x times v plus 1 over v to the x. Okay? And so, let me call this 6. We're getting somewhat closer to a product representation for the gamma function, except we want to know what happens to this function g sub n of x as n gets large. So we're going to look at the behavior of this, and to do that, let's say, look at the derivative, actually, I want to say, let's use 5. Okay, use equation 5, which is this here. That. Use 5 to see that the derivative of the logarithm of g sub n of x is going to be just the derivative of what is log g sub n of x. It's log gamma of x plus n plus 1 minus the logarithm of n plus 1 to the x, which is just x log n plus 1, minus log n factorial. And now we can just differentiate this. The derivative of the logarithm of gamma of x plus n plus 1 is our psi of x plus n plus 1. So this is sine of x plus n plus 1. Oh, I should add something. For x greater than or equal to 1. So I want to assume x is at least 1 here. We get this is psi of x plus n plus 1 minus the derivative of x log n plus 1 is just going to be log n plus 1. and then this is a constant as far as x is concerned. So we're left with this. And now here's the point where I'm going to use the fact that psi is increasing. So I just sort of stated that without proof, but I'm going to use it here. Psi is an increasing function, and since we're assuming that x is at least 1, psi of x plus n plus 1 is at least psi of 1 plus n plus 1. So this is at least, I'll write it as psi of n plus 1 plus 1, just because x is at least 1, minus r log n plus 1. And now psi of n plus 1 minus log n plus 1, according to 5, if you just replace n with n plus 1, this is positive. Okay, so the derivative of the logarithm of g sub n of x is positive, meaning that the logarithm of g sub n of x is increasing, meaning that g sub n of x is increasing in x. So therefore, gn of x is increasing. And in particular, that implies that gn of the floor of x is less than or equal to gn of x, which is less than or equal to gn of the ceiling of x. And these floor of x and ceiling of x are integers. So let's look at what happens when we take g sub n of an integer. So I'll say for a fixed positive integer m, g sub n of m, by definition, this is going to be gamma of m plus n plus 1. But that's just m plus n factorial. So we can write this as m plus n factorial divided by n plus 1 to the m. Okay, and then n factorial. And we can simplify this a bit. We have an m plus n factorial over n factorial, and we can write that just as n plus m times n plus m minus 1 times dot 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 times n plus 1. And then we're still left with this n plus 1 to the m. And now I'll note that this approaches 1 as n goes to infinity, because this is just a quotient of two polynomials in n. Each one has degree m. The leading coefficients are both 1. You just, by calculus, this goes to 1 as n goes to infinity. So, what are we saying here? We're saying that for any integer m, gn of m is going to go to infinity, or is going to go to 1 as n goes to infinity. And so that implies that gn of the floor of x and gn of the ceiling of x are going to 1. So by the squeeze theorem, gn of x is going to go to 1. So, therefore, gn of x goes to 1 as n goes to infinity for every x greater than or equal to 1. So, this is useful because now we can see what happens when n goes to infinity in 6. So letting n go to infinity in 6, what do we get? All right, gamma of x, just by our functional equation, is going to be 1 over x gamma of x plus 1. That's just our functional equation for gamma. And then gamma of x plus 1 will be what we get here if we take n to infinity. This goes to 1, according to this. And then here we're just going to be left with the product from v equals 1 to infinity of this stuff here. So we have 1 over x times gamma of x plus 1 is just going to be the product from v equals 1 to infinity of v over v plus x, v plus 1 over v to the x. This is, I'll call this 7, and this is for x at least 1. Okay? So we have this product representation for the gamma function when x is at least 1, and we want to get this for any complex argument. So now, let me say, we'll consider S a complex number. And I'm going to sort of hand wave here and just say one may show that the product from v equals 1 to infinity of v over v plus s, v plus 1 over v to the s. So this is just this product here with x replaced by s. This converges absolutely and uniformly on compact subsets of, I'll write the complex numbers, take away the set of negative integers, which I'll write as z sub less than or equal to -1. So I've taken away the negative integers just because I want to avoid the poles that come here from the denominators 1 plus s, 2 plus s, and so on. And then the way you do this is pretty straightforward. Basically, you look at the logarithm of this and you get a sum of logarithms. You can pick some compact subset of this and you end up with just the sum of these logarithms on a compact subset. You can bound them in a fairly straightforward way and show that they converge absolutely and uniformly, and then that'll imply that the product also converges absolutely and uniformly. So that's not too difficult to do, so I'm just going to skip over it. But once we have this, this implies that, therefore, we can call gamma twiddle of s. This will be 1 over s times the product from v equals 1 to infinity of v over v plus s, v plus 1 over v to the s. This product defines a meromorphic function on C with poles, or with poles set, the set of non-positive integers. And I have included 0 in the pole set because you get a pole from this 1 over s term here. So this gamma twiddle thing here, this product is it's a meromorphic function on the complex plane with poles at the non-positive integers. We also know that our original gamma function is a meromorphic function on the complex plane with poles at the non-positive integers. And these functions agree, according to 7, when x is at least 1, when x is a real number at least 1. So by the identity theorem, they are the same function. So by 7 and the identity theorem, gamma is equal to this gamma twiddle. Okay, so this gives us a product representation for the gamma function, and as an immediate consequence, we have a theorem. Gamma is 0, free. Okay? And the proof is simply observe that gamma of s, or alternatively, this is gamma twiddle of s, is a convergent product. Remember I said it converges. So it's a convergent product of non-vanishing factors. And therefore it's non-zero. Okay? So, yeah, the gamma function does not have any zeros in the complex plane. So this is sort of the first thing that I wanted to go over. The second thing, the second major thing, is Stirling's approximation for the gamma function for a complex argument. So let me talk about that. This will be Stirling's approximation for gamma of s. So I'm going to have to hand wave a lot in this section just because there are a lot of details that go into this. Getting the product form for the gamma function over here it sort of took some time, and I think if I wanted to go through the derivation of this in detail, it would take at least 50 minutes by itself. So I'm just going to sketch the main ideas. So let me start by defining the Bernoulli polynomials polynomials b sub m of x by t e to the tx over e to the t minus 1 is equal to the sum from m equals 0 to infinity of b sub m of x t to the m over m factorial. Okay, so as I've written this, it's just defined as by this generating function equation. And as I've written it, I don't think it's immediately obvious that these are going to be polynomials, but they are polynomials, and they're called the Bernoulli polynomials. So I'll just say this is a definition. And now, also the mth Bernoulli number is b sub m, which is defined to be just the constant term b sub m of 0 in the Bernoulli polynomial b sub m of x. Or if you like, just set x equals 0 here, and you get t over e to the t minus 1, and that becomes the exponential generating function for the Bernoulli numbers. Okay, so the reason I've done this, and this is the part where I hand wave a lot, the reason I've done this is because there's this powerful tool technique called the Euler-Maclaurin summation formula, and it is a powerful tool that you can use to get formulas for things, and I'm not going to go into any detail explaining what it is or how you use it or why it's coming into play here. I'm just going to say that we can use it to get the following. So using the Euler-Maclaurin formula, we get, so if we use this, we get log gamma of s is equal to s minus 1/2 log s minus s plus 1/2 log 2 pi plus the sum, right over here, plus the sum from j equals 1 to m. M is some positive integer. Sum from j equals 1 to m of b sub 2j, the 2j is the Bernoulli number, divided by 2j times 2j minus 1, 1 over s to the 2j minus 1, minus 1 over 2m times the integral from 0 to infinity of b sub 2m of the fractional part of x divided by x plus s to the 2m. Okay, so this is why I didn't want to go into a lot of details, because that's kind of a lot. But this is true for any positive integer m. So in particular, we can take m equals 1 and see what we get. Let me call this 8. Let's take m equals 1 in 8 to get, what do we get? Log gamma of s is equal to s minus 1/2 log s minus s plus 1/2 log 2 pi plus, if we set m equals 1, this sum and this integral can just combine into something that I'm going to call omega of s. I'll call this 9, where omega of s is 1/2 the integral from 0 to infinity of b sub 2 of the fractional part of x minus b sub 2. So the Bernoulli polynomial here, this is the Bernoulli number, divided by x plus s squared dx. Okay. So this comes about just by this first part, the b sub 2 a fractional part of x over x plus s squared. This comes from this integral here, setting m equals 1. And then if you just calculate b2 and you integrate this here, it turns out that it's precisely equal to this. Or actually, you don't even need to know what b2 is. You just integrate this second part over here, and you end up with exactly this sum here. And so I'm not going to go into the details of that, but it's pretty straightforward to go through to see that those are the same. So we have this, and this is like our error term for Stirling's approximation. So we're going to try to get a bound on the error term. So let me say, now, you can calculate Bernoulli polynomials, and people have done that, and you can show that b2 of x minus b2 is just x squared minus x. So it's a simple polynomial. So b2 of x minus b2 is just x squared minus x, so 1/2 the absolute value of b2 of the fractional part of x minus b2 is no more than 1/8. This is just because you observe that fractional part of x is between 0 and 1. So here you're just going to maximize the absolute value of x squared minus x between 0 and 1. You end up getting 1/4. And then times the 1/2 gives you an 8. Okay. So from this, what do we get? Thus, the absolute value of omega of s is less than or equal to, just take the absolute value and crash through into the integral, and you get the 1/2 absolute value for this numerator here, gives you an 8. And we're left with an integral from 0 to infinity of 1 over absolute value of x plus s squared dx. Okay, so now let us suppose that our complex number s is sigma plus it, and we'll assume that this is not a non-positive real. So it is not a real number that is less than or equal to 0. And this is just because we want to avoid the poles of the gamma function. And if we do this, then the absolute value of our error term omega of s is less than or equal to 1/8 integral from 0 to infinity of 1 over, okay, x plus s is just going to be x plus sigma plus it, and the absolute value of that squared is just x plus sigma squared plus t squared. So this is x plus sigma squared plus t squared dx. And this we can actually calculate explicitly, and it's going to be equal to 1 over 8 sigma if t is 0 and sigma is positive. And it's equal to 1 over 8 times the absolute value of t times the arctangent of the absolute value of t over sigma if t is non-zero. Okay, so first of all, you can see why the arctangent is going to come into play here, simply because this integrand is the sort of thing that's going to give rise to an arctangent. It's like 1 over something squared plus something squared, so you can see why that's going to give you an arctangent. But it might be more useful, and I'll just make this a remark, it's a bit more useful to consider the arctangent of absolute t over sigma as simply the absolute value of the argument of our complex number s, which by convention is going to be less than pi. And that's really just exactly what it is, but it's sort of more useful to think of this in that way, first of all, because